All right, thank you everyone for joining us today. Good morning. Today is Monday, November 7th. First thing, I apologize. Today is Tuesday, November 1st, and my name is Greg Wadley, and I'm the Clear Roads Administrator with CPC and Associates. We're here today for the final closeout webinar for Clear Roads Project 1407, which is on identifying best practices for snowplow route optimization. This is a requirement for all Clear Roads projects that we conduct a final closeout webinar nearing the end of the project's duration, before the end of the contract period. Just a note before I turn this over to Jonathan Downs, who's the principal investigator on this project from the University of Vermont. We will be muting, we have muted everybody during this presentation. With a large number of people, it just becomes difficult to keep everybody and their background sound sort of quieted down during these presentations. So we're going to keep everyone muted. If you have any questions throughout the presentation, please enter them into the chat box. I'll put a note in there just to remind people as well, but all questions should go into the chat box in GoToMeeting. And then we will, at the end of the presentation, Jonathan will go back and go through those questions and provide responses to those. And then once we get to the very end, when there's basically no more questions, I'll unmute everyone and give one last opportunity for any questions that you might have. So with that, I'm going to turn it over to Jonathan, and Jonathan, you can go ahead.
Terrific. Thanks, Greg, and thanks to everyone for joining in on the webinar today. As Greg mentioned, this project is on identifying best practices for snowplow route optimization. And it was conducted by a team primarily at the University of Vermont, myself, my colleagues Jim Sullivan and David Novak, and Darren Scott, who's at McMaster University. Just to give you a sense of where we're going today, I'd like to keep this to about 45 minutes to make sure we give time for questions. I'm going to start with a brief overview of the purpose of this project and also the snowplow optimization routing survey that we distributed as part of task 1 of the project. Then I want to talk about the 2 types of tools that we encountered through the survey and through our interactions with different maintenance organizations, and those are route review tools and route optimization tools. And there are 2 different ways that winter maintenance agencies are using to improve their routing, and they have some distinct features that I think it's important to separate. After that, we're going to be talking about some of the steps that compose a typical route optimization project. So in a general fashion, what does it look like to undertake route optimization for a given area? Many of the lessons plug into particular steps here. So I think just going through and saying, hey, this is what it looks like. These are the really 5 core steps of a route optimization project. Will give us a solid grounding as we move into the routing case studies. And this is 9 deeper digs that we've done into DOT and also a couple of Department of Public Works efforts at route optimization. I then have a series of conclusions related to the potential savings from route optimization, some best practices to ensure that these projects are successful, and some potential pitfalls that have caused hiccups in several of the projects focused here, and then just a few final thoughts to wrap that up. So just to recap the project purpose, what we're really trying to do here is we're trying to provide winter maintenance organizations with some guidance and help on how they can think about route optimization. Think about what are the best practices that make route optimization projects successful, especially what kind of commercial off-the-shelf optimization software options have been applied successfully by DOTs and other winter maintenance organizations. Documenting the pros and cons of each of these packages, thinking both about ease of use and the capacity to incorporate real-world operational constraints. And not to jump the gun here, but the single biggest key that we found to successful route optimization is not in fact the software, but it's the collaboration between the optimization team and the DOT winter maintenance experts. you have two groups here, often with some real different areas of expertise, and if you get close collaboration and good communication between those two teams, you can make sure that the optimization results, the routes that are outputted, make sense in a real-world application and are something that can be implemented by winter maintenance professionals. So one of our first tasks for this project was a snowplow routing survey. The purpose of the survey was to determine what features of a route optimization software are most crucial to winter maintenance agencies. So these are things like the ability to reflect actual vehicle material capacity constraints in the optimization. So how much salt or brine can your vehicle hold, and therefore how far it can travel before it needs to reload those materials. A whole host of things related to lane-specific routing and other issues like that. Once we know these, we can then evaluate a set of software against them and say these are software that successfully incorporate these, or watch out, this is a feature that maybe can't be done in a particular software package, and if that's important to your agency, you might want to look at a different one. And the second part of the survey was really to identify the transportation agencies that had recent route optimization experience. In order to identify these best practices, we wanted to find a set of agencies that have been working in route optimization recently, and that could really give us the lessons learned here. So to recruit for this survey, we sent out an email invitation to ClearRoads members. We also distributed it via the AASHTO Winter Maintenance Listserv, and did direct emails to all of the Canadian Ministries of Transport to try and get some of the international experience in this area. The survey had an open link, which means you didn't need a password or a specific link to get into it. So we did encourage people to send the survey to others within their network, what's known as a snowball recruiting method, to ensure that we were getting as many of the agencies that are active in this area as possible. Overall, there were 49 individuals who took the time to respond to the survey. They represented 31 different agencies. We were quite pleased with both the number and the spread of these respondents. It included 33 respondents from U.S. state DOTs, 7 from Canadian provincial DOTs, 5 respondents from towns and local departments of public works, as well as a few responses from university consultants and other types there. On the map here, the shaded states are the states which reported that they were something other than simply using expert judgment for their route optimization. So these were respondents that we targeted for the second part of our survey, digging in depth into the specific projects to get our lessons learned and best practices. And the red star there is the village of Niles in Illinois, which was the one Department of Public Works responded that said, "Hey, yes, we've done something in this area." It was pretty gratifying. We got a number of follow-up emails from people asking about the final report. So clearly, this is a project area that the people are interested in. And we even had somebody from Alberta, one of the operations managers, who took the time to send in an email and said that he couldn't take the survey right now because his office was evacuated to deal with a wildfire, which I thought was really above and beyond on his part. So the first thing we asked agencies is, how important are different optimization goals to your routing efforts? And we gave 2 options here. One is minimizing the time until all roads have been serviced, or a subset of roads, your priority 1 roads, etc. And the other option was to minimize the total vehicle hours of travel. Both of these were rated as very important features by more than half of the respondents. It is important to note that while both of these, both the service time and the total vehicle hours have traveled, might be improved by a route optimization project, they can't both truly be minimized at the same time. And so just to give an example of that, in example A here, we're minimizing the time until all roads are cleared. So we have a garage with 2 plow trucks, red and blue. The red plow truck is servicing this east-west road, and the blue is deadheading to a north-south road servicing that, and they're both returning to the depot. So here we do have some overlap between the routes, some deadheading, so that increases the total vehicle hours of travel relative to scenario B, in which only a single vehicle is used to cover the entire network, traveling to the north-south road, servicing that, and servicing the entire east-west road individually. Now, depending on the performance constraints that you put on the optimization, it may be that the only way to hit your target is to route both vehicles, in which case both of these will converge to the same answer. But just something to keep in the back of your head, that optimization projects can have different goals, and essentially those boil down to completing all winter maintenance, all snow and ice control operations more quickly, or doing it with the true minimum amount of vehicle hours of travel, completely reducing and eliminating route overlap in all cases. We also asked, as I mentioned, what features in a route optimization are most important to your agency. I'm going to focus here on the top 5. In the full final report, you can get additional information about all of these, but for the purposes of brevity here, we'll focus on the top 5 most important features. The first of these was that this software should account for roadway prioritization schemes. Almost all winter maintenance agencies include some prioritization in terms of what roads have to be serviced in what time frame, what roads need to be serviced first, and so that's an important feature. The ability to allow vehicles to resupply at a remote storage facility was also rated very highly by a number of respondents. As I mentioned previously, accounting for vehicles with differing salt or other anti-icing, de-icing friction materials was also very important. Most vehicle fleets are not uniform. Vehicles have different sizes and different capacities. Lane-specific routes for multi-lane roadways was listed as very important, as was checking the compatibility between vehicles and roadways. So some roadway infrastructure, for example, roundabouts or ramps, may limit the maximum size of a plow that can service it. In other cases, in an interstate with a wide shoulder, you may want to make sure that your largest plows are there. So that was another important feature. And then I'll just point out that 4 of these potential features were really about scenario-based routing. One way or another, do we want a set of routes, a single set of routes for all scenarios that district managers can modify on their own, or do we want routes that account for storm conditions, that account for shortages in equipment, that account for modified levels of service because maybe it's overnight hours? And I'll return to this later in the presentation, but it turns out that it is somewhat of a challenge to do this type of scenario-based routing. So as I mentioned, we discovered that there are really 2 types of route improvement projects that are going on in winter maintenance agencies right now. There are route review projects and route optimization projects. Both of these have been used successfully. They require some similar inputs, but they're also different in some fundamental ways. So route review projects rely on tools that display existing routes, track route mileage, cycle times, other route characteristics, and facilitate expert route revision. So these let winter maintenance professionals very clearly see what their routes look like, how long they take, and then identify themselves ways that those routes can be modified and to improve performance. Route optimization projects, in contrast, use mathematical algorithms to generate whole new sets of routes. These do some sort of cost minimization, and they use mathematical solutions that generate approximate solutions. So it's not, though it's called a route optimization, the results are not necessarily perfectly mathematically optimal, simply because that math remains too hard for our computer systems. So it gives you good routes, but not necessarily perfect routes. So for a typical route optimization project, and this is again focused on the optimization projects, not the route review projects, you're really looking at 5 steps once you've decided that you want to undertake this project. The first step is selecting a project team, as well as the software that you want to use for the optimization project. There are a number of considerations that can go into this: what sort of staff expertise is available, what sort of software licensing an agency may already have, and what sort of software features you are looking for. In 8 of the 9 projects that we reviewed here, agencies opted to use external teams, by and large, to conduct the route optimization. So that's one decision point, and it depends on who you have on staff and what their capacity is. Software licensing can be important. So when we get to Utah DOT, who's one of our example projects, they opted to use the program Esri ArcGIS because they have used it for a number of their other agency projects, and so they wanted to maintain that consistency. The next step in the process is data preparation, and this actually looks pretty similar regardless of the software that you end up using. The big piece here is creating a base routing network. So you need a representation of the roadways that you're plowing. You need to have information about how quickly your plows travel across each different road segment. You often need to represent each lane within a roadway individually on the map. So instead of having a single line that represents 2 or 3 or 4 different lanes, you'll have 2 or 3 or 4 different links physically on that map. Typically, the network also includes information about material spread rate for each link. The routing network would also include the location of garages from which vehicles can be routed, and designations on what roads need to be serviced. So if you are a state DOT and the routing network includes local roads, you would have a flag on those local roads if they are not roads that you are servicing. And in some cases, you might want a flag on them that say you don't even want your vehicles traveling on them. You also need to provide fleet information. So how many vehicles, where are they located, what type of material capacity do they have, are there restrictions on what roads they can service, are they too large for some roads, too small for some roads. And then you get into the route optimization itself, which is running that software that you've selected. There are a number of options within that software that can typically be selected, restrictions on vehicle turning behavior, material spread rate, a whole host of features like that get selected in consultation with the winter maintenance professionals on the ground. And then whichever proprietary algorithm is within that software package, you run that, it outputs a set of routes. These are generally provided both visually, a map that shows road lengths highlighted by route color, and also tabularly in a turn-by-turn directions, and those can be inputted into a variety of GPS devices, for example. The fourth step is taking the time to do route review and route revision, and this is really where the practitioner knowledge comes into effect. Every single project that reached the implementation phase that we reviewed included significant time for this step. It's where practitioners can say that turning behavior is unsafe, it's impractical, that vehicle shouldn't be on that road lane, and it's really what takes this from a theoretical set of routes to a set of routes that are practical and implementable. And this often can involve dealing with practitioners at a variety of stages within the winter maintenance organization. So starting with supervisors and going all the way down through vehicle operators to make sure that local knowledge and that knowledge of the on-the-ground realities of snow and ice control are incorporated into the routes, and you don't end up with things that are impractical or unsafe. And then the last step, of course, is actual route implementation, and this takes a dedication to the project, a dedication to see those through and ensure that they are realized on the ground. So as I mentioned, we looked at a total of 9 different route improvement projects for this study. They include 2 of what we're calling route review projects, one done by Pennsylvania DOT and one done by Iowa DOT, and 7 route optimization projects that actually do that algorithmic route generation. 5 of these agencies were identified by the Clear Roads team in advance of the project. That was Pennsylvania DOT, Iowa DOT, Indiana DOT, Utah DOT, and the Vermont AOT. And then 4 additional agencies, Centennial Colorado, Niles Illinois, Wisconsin DOT, and the Kentucky Transportation Cabinet, were identified through the survey process. We've got a number of different softwares represented here. So Pennsylvania DOT is using a custom tool that was developed by GeoDecisions in consultation with PennDOT. 3 of our optimizations used a product called Fleet Route that's distributed by C2Logix. 2 used Esri's ArcGIS. Indiana DOT used a custom software package developed by Purdue University, and the Vermont Agency of Transportation used Transcat, a GIS software that's developed by Caliper. And we'll get into all of those individually. So Pennsylvania DOT undertook a project in 2012 to assess process and operational efficiency. And what the Winter Maintenance Division found very quickly is that there were some data gaps, and that it was difficult to pull together all of the information across all of their districts and counties. They collaborated with GeoDecisions to create a custom planning tool that had a GIS component that made it very easy to visualize what was happening, as well as a bunch of tabular information about their vehicle fleet, their material spread rate, etc. From a routing perspective, the big benefit of this project was that it made it very easy to identify disparities in route length, and that facilitated the ability of district managers to do some route balancing and therefore improve the performance of their snow and ice control. Additionally, this database allowed for the comparison of salt application rates across jurisdictions, which has been something that had been difficult to do before, and it dramatically reduced the time required to produce route maps for each service territory. Some of the key project lessons here were that knowledge transfer and quality assurance are very important. So this project was successful because the information that was produced by it was useful to the managers on the ground, and therefore they were really good about feeding information back into it. So that's been an ongoing back and forth to maintain that data is up to date and high quality. Iowa DOT is also doing some route review work using their AVL GPS system, which is provided by Skyhawk Telematics at this point. Specific to routing, having validated data on route length that's true on the ground, time and distance that each vehicle takes, again, facilitates the ability to look at routes and say, are these out of balance? Are there revisions that we can make? At the same time, Iowa DOT is exploring some additional route analysis services with Skyhawk. And so that would then move more into the traditional route optimization type project. Now, I know that Clear Roads recently wrapped up an ABL GPS project, and so probably many of you are familiar with the types of benefits that you could have from an ABL GPS system independent of the routing, and that includes things like tracking material application rates, tracking engine diagnostics, sharing the location of your plows with the public in a way that can really help increase trust in the agency, provide good opportunities for driver training, and a whole bunch of quality assurance purposes there. As we move into the route optimization projects, I just want to highlight the 5 optimization features that agencies said were most important to realistic on-the-ground routing for them. So again, these were route prioritization, taking into account roadway prioritization schemes, the ability to resupply vehicles at remote locations, the ability to model a mixed vehicle fleets where different vehicles have different salt capacities, lane-specific routing, and vehicle roadway compatibility. The green checks here indicate that a feature was incorporated in a specific project, whereas the tilde indicates that it was not, and in most cases that was because it was not identified as an important feature for that specific optimization. So for example, for the Centennial Department of Public Works, the remote material, the remote material resupply was not an important feature since the agency only has a single garage and no remote location to resupply at. For Wisconsin DOT, in the 3 counties that they did their initial pilot testing in, there was not a route prioritization scheme that needed to be incorporated, so that option was not included, though it is included in the software. So just to go back one step, the Centennial Department of Public Works, the Niles, Illinois Department of Public Works, and the Wisconsin DOT all did their routing with Fleet Route by C2Logix. The Vermont Agency of Transportation project used Transcad by Caliper, and the Kentucky Transportation Cabinet used ArcGIS. The one software feature that simply was not available, as well as not being implemented, was that Transcad did not include an ability to reload vehicles at remote locations and continue to service demand. Otherwise, the feature set across these softwares was fairly consistent. So Centennial, Colorado has really been one of the very public successes for route optimization. The project was undertaken in 2011, 2012, using the Fleet Route software by C2Logix, and it was the C2Logix team that did the optimization. A real highlight of this project was that it was iterative and incorporated feedback from supervisors and operators in a multi-phase optimization process. So C2Logix generated a set of routes. Those were provided to the supervisors who identified potential problem areas, mostly in terms of turning behavior. That was incorporated back into the optimization process. New routes were generated and sent down to the driver levels who tested those routes outside of winter conditions and continued to identify potential problem areas for manual revision. The project showed a significant reduction in the time to complete snow and ice control operations, on the order of 28 to 40% reduction in total time. This was measured across a couple of storms in 2011 and 2012. A little bit difficult to get more detailed than that because the existing set of routes in Centennial were fairly poorly documented, So that part of the pre-post comparison is a little bit fuzzy. One of the key takeaways that I got from talking with the C2Logics and CH2M Hill teams is that assessing the degree of route imbalance can provide some insight into the potential for route improvement. So in this case, they did a histogram of route lengths and saw that their route lengths were in fact quite imbalanced, and that was one of the reasons they had confidence that a route optimization project could improve their current performance. I have Niles, Illinois Department of Public Service on the same slide here because they are using the same software and the same project team. This is a project that's currently ongoing now. There was some initial implementation in the winter of 2015, 2016, but those routes are still being revised a little bit. It was also a very light winter, so there was not a lot of opportunity to test them. Some of the takeaways there are that real-world restrictions that are a fact of life for winter maintenance personnel are not always apparent to folks doing route optimization. It's simply a different set of expertise. And so in the first set of routes that came back, Niles identified a series of problems related to turning behavior and to the match between vehicles and roadways that required some pretty significant revisions. U-turn restriction implementation is pretty important. Here, one issue they had was that when they prohibited U-turns, their vehicles would continue to travel quite a distance into adjacent towns in order to find a safe turnaround location. But when they allowed U-turns, plow trucks would cross multiple lanes to make a U-turn in a way that was not safe. And again, with this project, as with the Centennial project, it was a little difficult to make direct comparisons between the new and old routes because there wasn't great data availability about the performance of those old routes. Wisconsin DOT is the only agency here that is undertaking their route optimization project in-house. They're also using C2Logics Fleet Route, but that is the project team is composed of Wisconsin DOT staff. There are routes that are planned to be implemented for this coming 2016-2017 winter. And they're piloting this initially with 3 counties, so they also hope to have a few more completed before this winter season. For those routes, they have seen a reduction in route length by an estimated 4 to 10%. And one of the really big successes is that in one of their counties where they had a 23% increase in lane miles due to some major capital improvements, the more efficient new routes allowed them to avoid purchasing additional trucks to service those new lane miles while still meeting their winter performance targets. The key takeaway here, and this is really true across many of the projects, is that post-processing the routes that are generated by the optimization software takes longer than the optimization process itself. It takes real significant staff time to look at the routes, to say this is where there are or are not problems, and then to do that manual review and revision process. The Kentucky Transportation Cabinet and Utah DOT are both making use of the Network Analyst tool in Esri's ArcGIS. The Kentucky Transportation Cabinet is doing this in conjunction with a team at the University of Kentucky, while Utah DOT is using an external consultant team's Spatial Matters. Utah is a little farther away from route implementation, so I'm going to focus a little more on the Kentucky Transportation Cabinet experience. This has been done so far for a single district in Kentucky. I believe it's their District 7. And the initial estimates of the time reductions generated by the new routes is approximately 8.4% relative to the existing routes, although those routes are still undergoing some revisions. one of the key takeaways from the Kentucky Transportation Project, is the importance of devoting significant time to getting a really good base routing network. That process can be time-consuming, but as your network improves, your optimization results improve, and you can save some of that time on that review and revisions because the outputs are more practice ready. For Utah DOT, in their first pass through looking at routes in the Ogden to Provo area, there were some issues with the speed assumptions that went into that, and consequently, when those routes were passed down to the managers and operators, they weren't seen as being realistic to on-the-ground scenarios. So again, making sure that you have good inputs increases the quality of your outputs. The Vermont Agency of Transportation actually undertook two optimization-related projects. The first was a route optimization project, and the second was a facility location project. The project team for this was myself as well as my co-authors on this review, and we used the commercial off-the-shelf software package, Transcad. So this project was a little bit different from some of the others here in that, in addition to looking at just the routes themselves, we experimented with several different vehicle allocations based on the road miles for each garage and road miles weighted by road importance. We also did a territory optimization to make sure that all roads were served by their closest garage, and did scenario-based routing to include a variety of salt spread rates, and generated, I think it ended up being 9 different sets of routes across the different vehicle allocations and salt spread rates. We also did an analysis where we looked at how far each section of road was from its nearest salt facility, the nearest place that a vehicle could reload on salt. This was subsequent to the routing process, so these locations were not fed back into the routing. And so we can see here, these red areas are most distant from salt facility locations, and the project did identify a stretch on Interstate 89 that was distant from the local garages, and where there was a closed rest stop. That was a good target for a remote salt storage location, and the agency is moving forward with that, so that was a positive outcome. There was also some rearrangement by the Agency of Transportation to get some additional vehicles in one of the high priority regions. In this case, the routes themselves were not implemented by the agency, and I think there are 2 big takeaways here that are important to share about what a barrier to that was. One was that this extensive scenario analysis, where we generated 9 different set of routes, made it difficult to compare the project outcomes to what's happening on the ground currently. And also, this extensive set of scenario analysis made it difficult to transfer knowledge to the agency in a way that was easily actionable by the agency. It simply wasn't feasible to do the level of route review for all of those different routes that's necessary to get on the ground routes out of an optimization process. Something we look forward to continuing to work with the agency on in the future, to make sure that they can get some really actionable data out of this on the route side, as well as the facility location, vehicle allocation side. The final study that I want to talk about here is by Indiana DOT. Indiana DOT was really one of the very, very early adopters of route optimization technology. Their project goes all the way back to 1993-94, and a custom software package developed by a team at the Purdue University. It's the Computer-Aided System for Planning Efficient Routes, or CASPR. The project had some initial success. It looked like it would be able to reduce winter maintenance fleet size. It did, as with other projects, require a considerable amount of manual revision to the routes. It sounds from what I read and from talking to to folks at Indiana DOT that with this older software packages, those revisions were even more extensive than they are with the more modern software packages. And so, in fact, 28% of the routes were infeasible for implementation even after extensive review. So there was a real barrier there in terms of how close they were to actionable and whether or not you could get them to that last step. Casper isn't used by Indiana DOT anymore, and there's some real challenges with maintaining institutional knowledges about custom software applications. So this was something that, as I said, had a good initial rollout, but the challenges of using the software and the challenges of maintaining institutional knowledge of something so specialized made it so that it wasn't something that was ultimately continued by the agency. So some key conclusions here. One, route optimization and route review can generate savings for transportation agencies. In the three implemented projects, we saw savings in the approximately 10% range for two and up to 50% in the case of Centennial, Colorado. The degree of savings, of course, depends not just on how good your new routes are, but the quality of your existing routes. So in Centennial, Colorado, they knew that their routes had some inefficiencies because there was a real spread in their route length. So if you look at existing balance within your routes, that can be a good way to say, hey, is this a project where we're likely to see some benefit? If your routes are fairly similar in length in terms of performance time, there may be less opportunities for savings. If there's a wide disparity there, there's probably more. Optimization packages that we looked at offered a fairly similar set of features, but software is not enough on its own. So we've got some additional best practices and pitfalls that relate to that we'll cover in just a moment. I also want to emphasize that we think that these lessons, which we drew from the four optimization packages we looked at here, are likely applicable to other software packages as well. It is really project lessons, not software lessons. And back on the software again, that of those top 5 features, 2 of the 3 off-the-shelf software packages offered all five features. Transcad offered 4 of the 5 features, but did require some additional custom scripting for the Vermont application due to the optimization criteria that it applied. Another conclusion is that AVL and GPS systems are highly complementary to both route optimization and route review projects. These can help provide really good input data because you know on the ground how long each route takes, how quickly vehicles are traveling, which is key to both route optimization and route review projects. And it's also helpful for the implementation of these systems. If you're feeding your drivers a whole bunch of new routes, being able to plug that directly into the system so that they have turn-by-turn directions makes it much easier and more feasible to help drivers learn a new set of routes. Finally, before we get to the best practices section, there's still a number of challenges related to the dynamic and scenario-based routing, which a number of agencies expressed an interest in. Essentially, this boils down to the time for review and revision that we really feel is key to get any optimization implementation ready is significant enough that having a large number of scenarios that you have to do that for is a pretty significant time sink and may be a challenge in terms of agency resources. And again, if you don't have an AVL GPS system, having a whole bunch of different routes depending on weather conditions and equipment availability may present challenges for drivers as well. So on to some of our best practices from these projects. The first one, which I think we've hit a couple of times and is really, really worth emphasizing is that close collaboration between winter maintenance professionals and the optimization teams is absolutely essential. The modelers who are doing optimization type projects do not necessarily know the details of the on-the-ground reality of winter maintenance. And so they might not know what questions to ask to get the right inputs to an optimization. Similarly, folks who are working in winter maintenance are not experts in optimization and don't necessarily know what questions to ask the modelers to make sure that all of those are incorporated. So in our potential pitfalls section that's coming up, I've tried to highlight some common areas that have caused hiccups in the projects featured here to help sort of bridge that gap so that people who are looking to do these projects can say, okay, these are the kinds of things we need to be thinking about. These are the kinds of things we need to engage in, and that should be true throughout the project, that there's good communication back and forth to make sure that those important features are incorporated in the routes. The second best practice is that you need to devote time to generating a snowplow routing specific base map. The better that representation of the road network is, the better the output routes are. And we'll have a number of specific examples of that in the pitfall section coming up. But this is really time at the front of the project that pays off at the end of the project. And finally, computer-generated routes are never perfect. Regardless of the collaboration, regardless of the time spent generating your network, expect to have to review those routes and allow times for revisions. This is where you go from helpful routes to actually implementable routes, and it's a really key step. So as far as potential pitfalls, the first one is insufficient understanding of operating constraints by the optimization team. So you need to make sure the optimization team has a clear understanding of acceptable snowplow turning behavior. Where are U-turns acceptable and not acceptable for your plows? Do you want to impose a turn penalty for left-hand turns? Do you want to ban those altogether? Does that vary by intersection? What kind of time penalties do you want to impose on those left-hand turns? The more time spent hashing out exactly how you want the vehicles to behave, the better the output will be. Vehicle roadway compatibility restrictions are also important. This came up in several of the projects that we looked at here. That included the Niles, Illinois Department of Public Service project, where they had trucks going down alleyways where their plow would literally have been scraping the brick on each side. It included also the initial routes generated in the Kentucky project, where large triaxle trucks were going down some of the smaller state highways where they were not efficiently utilized. So talk about where there might be those restrictions so that gets incorporated into the modeling up front. Realistic vehicle operating speeds are really essential to good model outputs. Especially you want to be thinking about the minimum operating speed. So given a heavy snowstorm, how fast can your vehicles be traveling? You don't want to use the plow speed for a pretty light storm with a low spread rate where the vehicles may be traveling quickly. If that's the assumption, and then you try and apply those routes when the vehicle is traveling more slowly, the optimization really isn't going to hold under those conditions. And this was something that Utah DOT raised in particular, as well as a few other projects. Another issue that came up was the tendency of software programs to route snowplows across local roads or roads that were outside of their jurisdiction. And this is something that can be dealt with by adjusting the speed on local roads or just flagging them all together as being travel on them as being prohibited. So that's another area to talk about upfront to make sure that it gets incorporated in the routing. A few specific mapping examples here to show what some of these problems look like in the optimization project. This is one that we learned about pretty quickly in our project here in Vermont. This is Interstate 89, just north of where I'm in Burlington, and there is north of the intersection here, there is a crossover place where plows can safely change direction. This middle map here is the base map that comes with Transcad, and you'll note that crossing point is not included there. That's not uncommon for many commercial sources of mapping data, that they will not include restricted sections like that. They're not part of the public roadway. So you need to make sure that those get included in your base routing network. Otherwise, you're going to have plows, traveling all the way to the next exit to come down and service ramps. So that was something that we discovered in Vermont, and I'm sure other folks have run into it other places as well. Similarly, you have to look at what's happening at jurisdictional boundaries. So as I mentioned in the case of Niles, Illinois, one of their complaints in their initial set of routes was that their vehicles were taking extensive detours into adjacent towns. And essentially that was because the turnaround options at boundaries were not well represented. These can be a number of things, whether it's a side road, whether it's an off-road turnaround. Generally, that's something that's negotiated between the jurisdictions to make sure that there's no coverage gap. So here's Route 5 exiting Vermont. You can see where there's an off-road turnaround location, and just very simply here, you can encode a turnaround into the map that's right there, so that the plow truck does not keep going into adjacent areas for an unrealistic amount of time. Travel speed assumptions are also important as far as where vehicles are routed, and failure to accurately represent those speeds can result in inaccurate route durations, as well as failure to meet performance standards. This example here shows on the left, this is a route that takes a plow across a set of local roads because it is faster from A to B to go there than it is across the state roads. And so you can simply adjust within your base routing network the speed on those local roads to reduce them, to really discourage that kind of behavior. So there again is something that came up in several projects that actually has a fairly simple fix within the optimization if everyone's aware ahead of time that that's a potential problem. We have a few more examples of these in the final report, where you can look at some common problems and ways to avoid them, but just to get people thinking about what kind of conversations you want to be having with the folks conducting your routing projects. So just the final really key takeaways here. Route optimization has produced some documented savings across a number of projects, and we've got some additional projects that are going to be implemented soon, and they're going to be nearing completion. So there'll be new data points about this coming out over the next several years. In addition to the projects that we looked at here, Ohio DOT has a project that's ongoing. Illinois has a project that's ongoing. Vaisala has been working with Colorado DOT. So there are a number of projects that will be bringing more data points into this. The second thought is that post-processing can be reduced, though not avoided, through that careful collaboration in the optimization preparation phase. So that's good communication between winter maintenance professionals and the optimization team. And the last one is that many of the current optimizations assumed fixed service territories and facility locations. In fact, the Vermont project was the only one that looked at service territory boundaries. So there are potential for additional savings by some service territory and facility location optimization, though it can be challenging to change too many variables at a single time. But there is possibility for savings there. So that's our assessment of the state of snowplow route optimization. We think that the best practices are really going to be applicable across a wide range of projects, and following them will help people get to an implementation stage and not have their project peter out before then. At this point, I think we have a little bit of time for questions. So if If you'd like to enter those in the chat box, I'd be happy to answer them as best I'm able.
Thank you, Jonathan. I appreciate that. It was a really good presentation. We do have a couple questions in here. The first one was from Scott Lucas of Ohio, and he was asking, why are some of the states hash marked in that? I believe he's referring to that first map that you had in the presentation.
Yeah, great question. The hash mark states were states that had undertaken a computer-aided route optimization or route review. So they were states that were using some kind of tool currently. The states that were in blue were potentially doing manual and expert revisions to their routes, but hadn't taken that leap to using some of these computer-aided tools that we're trying to review here.
Okay. The second question is from Clay Adams of Kansas, and he was asking, were you able to get any cost information from the states that hired a consultant or purchased a software package?
Again, great question, Clay. That was not something that we had in our evaluation matrix. For projects like this that are done by a consultant team, the cost is going to vary a lot depending on the size of the area being optimized. So we had some projects like the Niles, Illinois project that, it's really a very small city. The Vermont project looks statewide. Wisconsin is rolling it out county by county. So I'm not sure we'd be able to get a great apples to apples comparison there, but I can reach out to those project folks and see if I can include that in the final report.
Got another question from Craig Bargfried of Iowa, and he asked, we're also related to that map, I believe, what do the yellow stars represent on the map?
So yellow stars were cities that responded, Departments of Public Works, but that had only done that sort of manual review. So again, they're the equivalent of the blue unhashed states. So as you can see at this point, it's really only a minority of agencies that are doing anything other than using expert judgment.
Question from Ken Hahn asks, I did not hear much about equipment solutions. Single front plows, two-way plows, wings, tow plows should all play a part. I think that was more of a comment.
Yeah, and I'd be happy to address that. As you get into the lane-specific routing, that's really where that comes into play. So if you have a wing or a tow plow that allows a single truck to cover multiple lanes, it's in that lane specification and in the base routing map where that plays out. But I agree that all of those are an important component of that.
Clay again from Kansas noted that he's not sure why Kansas is colored blue.
Clay, I think we got a response from. Did you complete the survey? Well, I think we had a response from someone in Kansas, Clay. So it's the hashed ones that are doing something optimized, and the flat blue responded to the survey, but didn't necessarily use a software package.
All right, I think that's the extent of the typed in messages. We have about 1 more minute. I'm going to go ahead and unmute everybody. If there's any last questions that you might have, we can go ahead and ask them now. All right, doesn't sound like anybody has any other questions. So I want to thank Jonathan again for his time on this project. The draft final report is out, it's being reviewed. Some of the comments from this webinar will go toward the revision process for that final report, in addition to the subcommittee's direct comments. And we should have that ready to go by the end of the month. I believe that's correct, isn't that, Jonathan?
I believe that's the target, yep.
Yeah, so we'll have get those comments in very shortly, and then we'll have the revisions to that, and the final report will be done. So this webinar will be posted on the Clear Road's website on the project page by the end of this week or early next week, and then the final report will be done and ready to be posted on the project page, probably, like we said, by the end of the month or early the following month. Okay, so with that, thank you so much again for Johnson, your work on this, and for everybody's time, and have a good rest of your week.